today will be the chemical kinetics and what is the need of studying chemical kinetics. See, we feel that there are some important, very important lessons which are withdrawn from the chemistry portions, like P block is withdrawn out. Chemistry has like the portions in chemistry has come down because of the mere elimination of the P block. So still this lesson remains. So out of the physical chemistry lessons, solid state is taken out, chemical kinetics, electrochemistry, and solution stays. So we need to understand as to why, what is the importance of chemical kinetics, which probably even CBSE thought that it should be kept. So chemical kinetics somewhere is going to help us to understand the chemical reactions. So as you can see, there are, why should we learn chemical kinetics? What are the aspects of learning chemical kinetics? Is to obtain knowledge on scope of chemical kinetics, to understand the aims and objectives of teaching chemical kinetics. Let us understand why we need to teach. And by just taking 2 or 3 examples, we will be able to understand why chemical kinetics is all the more important. To examine, let us just analyze the need and significance of teaching chemical kinetics. What are the values that can be communicated by teaching chemical kinetics? Okay, towards the end of the session, maybe the values which we try to know, weave in into the lesson will be try to strike a balance between the various parameters that affect our life. Chemical reactions are no way different from our reactions to our scenario, our surrounding, and our reactions also should be balanced. So I think that is the main value that we are going to carry at the end of this lesson. The yield is best when there is the best balance between the various parameters. So basically, so what we will do is I've listed out the learning objectives towards the end, because we normally know the the learning objectives is something which we take up in the beginning, right? To identify what the student will be capable of. But purposely I have put it in the end so that we, at the end of the session, will be able to see whether we have successfully done all these. So the students will be able to do a certain aspects of chemistry. So we will try to come to this part towards the end of this session. So let us go back to chemical kinetics. Okay, why chemical kinetics? I feel there are 2 angles of chemistry. One angle is the thermodynamics part, whether a reaction can happen or not. A reaction should be thermodynamically feasible. It's something like I stand against a wall and continuously push the wall. The wall may not move from its place. So thermodynamically, probably I have not exerted enough amount of energy to move the wall. Same is the reactions case also. Some of the reactions may not really happen in spite of putting our best efforts. Some reactions do happen, but they happen very, very slowly. So kinetics helps us to understand how fast the reaction would occur and what is the use of making the reaction to run faster. Do we end up getting better yield in a shorter time span? Are the reactions economical? Right? Kinetics tells us whether they are economical. Okay, I think before going into these, yesterday ma'am had some questions. Am I right, teachers? Some questions. So shall we try to recollect those questions? I think I forgot that aspect. There were 3 questions. One was that amino acids behave like salts. Am I right? They behave like salts.
Yes, ma'am. That's the first question.
That was the first question. I think more or less they are interrelated, the first and the second question. The second question that was given was 2-aminopropanoic acid and 2-chloropropanoic acid. Out of the 2, which one would have a higher? Let us put only the framework of the compound. If I can write only the needful things, then I see that it is a 2-chloropropanoic acid and 2-aminopropanoic acid. Out of the two, which one would have a higher melting point? I think these two are interrelated. What would be the answers, teachers, for this question? Amino acids behave as salts.
Every salts contain one acid, one cation and anion, ma'am. Just like that, amino acids in their ionic state, they contain both positive and negative charge, ma'am. In the isoelectric point, that's why amino acid can act as a salts, ma'am.
Very nice, sir. Very nice. Like when we talk about sodium chloride, the high melting point of sodium chloride is attributed to the high interionic attraction. In the case of amino acids of any kind for that matter will be able to have a Zwitter ion formation. So there can be an ionization of the H plus from this spot, and there can be an addition of a proton here to exhibit a Zwitter ion. Once there is a negative and a positive charge, the attractions are no longer covalent. Attractions are no longer van der Waals forces or dipole-dipole interactions. Instead, they go into the ion-ion category. And the ion-ion attractions are the strongest attractions that we see. So the melting points of amino acids are very high, attributing to the Zwitter ion formation. And because of the same fact, they are able to exhibit the salt nature. Very nicely summarized, sir. Can you connect these two, sir, with respect to same? The 2-aminopropanoic acid has got a higher melting point than 2-chloropropanoic.
Maybe hydrogen bonding, ma'am. Hydrogen bonding.
Yeah, okay. Hydrogen bonding is going to be there, sir. Like I told you, if the Zwitter ion had not been there, then we would have only dipole-dipole attraction. If it is not ionized, it is going to be dipole-dipole attraction or hydrogen bonding. So there is going to be hydrogen bonding. But in spite of that, the same Zwitter ion concept can be brought in. We can take away the hydrogen ion from here.
Can attach it with the NH2 group.
Yeah.
Then
so now,
charge is
now this can act as a Zwitter ion, whereas here it is a normal ionic bond, ionic compound. It acts as a carboxylate ion and a H plus. Am I right, Sindhu ma'am? Anything more than this?
Yes, for this you can add on this. Yeah. When it in the Zwitter ionic form, as you're saying, is right. And if you're just normally talking hydrogen bonding and lacking that in the because chloro, there you have an amino extra group. Right, Lakshmi, Zwitter ionic form.
So these two are interrelated. The third question was with respect to, I think, I again forgot the question. C2H7NO2. Yeah, H7NO2. Let us just take up this, and there was a question related to this, that that this compound exhibits three different forms as soon as the medium changes. So I think sir rightly told here that in neutral medium there will be a self-ionization, self-protonation. So if the medium is acidic, okay, and one more aspect was given, that this compound happens to be an optically active substance. So the moment there is an optical activity, I must see 4 different groups attached to an sp3 carbon. So this whole structure being connected with amino acids, I think we can quickly draw a structure. COOH, there is an NH2, there is a CH3 and a hydrogen. An sp3 carbon containing 4 different substituents lacks plane of symmetry and hence acts as chiral compound, and hence it is optically active. So can you tell us what will happen if it is put in an acidic medium?
The NH2 group is hydrogenated. That's why only COO group, CO minus only present, ma'am.
Okay. This is protonated, sir.
Protonated
will be protonated. On the other hand, if the H plus is coming from something like HCl, which is a strong acid, will this dissociate, sir? Will this dissociate?
No,
Do you
ma'am.
think- very good. So this is no longer CO minus. Instead, it's going to be a COOH. So common
ma'am.
ion comes into play, common ion effect. And what we see is only the cationic form.
Yes,
And
ma'am.
if at this stage it is electrolyzed, towards which electrode would it travel, sir?
With cathode, towards cathode.
Cathode, very good. And if the medium is basic, on the other hand, what would be the result?
The proton can be removed from COOH group, ma'am.
Yes.
That's why COO minus group is present, ma'am.
And the
That's why the ion is anionic, negative ion is created.
very correct, sir. And in such cases, it will travel to the,
To anode. That's why we can call it as anion.
and in neutral medium,
Neutral medium, there is no ionization because of the neutral pH 7. That's why the ion cannot move towards any electrode.
correct, sir, correct.
That is called isoelectric point.
Very correct, sir, very correct.
Thank you.
Okay, I think there is one more question that we normally speak of, that when I take an RNA and a segment of DNA, right? When I hydrolyze DNA, when I hydrolyze RNA, the number of adenines are always equal to number of thymines. The number of guanines are always equal to the number of cytosines. These are not double bonds, but and nor are they hydrogen bonds. They are just equal. Amount of adenines are equal to an amount of thymine. Amount of guanines are same as the amount of cytosines. Whereas when you hydrolyze RNA, the amount of adenine is no longer equal to, what should I write here? What can I write here? What would be the most accurate thing to write here?
Uracil.
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 Yeah. So the number of adenines are no longer equal to number of uracils. What does it suggest about the structure? What does it suggest about the structure of RNA and DNA? What does this tell?
Here in DNA, adenine is only connected to thymine, ma'am. In the same way, guanine only connected to cytosine.
Okay.
But here in RNA, that is not correct, ma'am. Maybe adenine can connect with any other adenine or some other groups, ma'am.
Okay.
In that way, only the adenine numbers are not equal to uracil, then guanine number also is not equal to cytosine.
So supposing there is an adenine on one of these strand, it definitely ensures that on the complementary strand there is a T. Adenine would be bonded to thymine. We know that DNA is a double-stranded structure. Whereas in the case of RNA, RNA is number one single-stranded structure, and at times it can just bond to itself. There is no guarantee that the entire RNA structure would be double-stranded. There is no complementary strand as such. So supposing there is an adenine, it does not guarantee that there would be an uracil. Yes, teachers, do you think this is right?
Yes, ma'am.
Yes, ma'am.
Yeah. So there is a double-stranded structure where one of the strand is complementary to the other. Whereas in the case of uracil, it is not so. At times the RNA coils up, but it is the same own strand which is getting coiling up. So I am just representing a straight structure. It coils up around itself. So there is no guarantee that the complete RNA would have a complementary strand, and hence the number of guanines may be different from number of cytosines. Number of adenines are different from the number of uracils. So I thought this one question also we had to discuss. Okay, coming back to our chemical kinetics. Chemical kinetics, as I said, talks about the kinetic angle of a chemical reaction. As I said, there are two sides of the chemical reaction. One, whether it is feasible or not, and the second is whether it is fast enough to give us enough products. Also, chemical kinetics helps us to understand certain mechanisms. as to where can we intervene into the reaction and bring positive changes, where can we improvise on the yield. So the kinetics angle is important for us to better the results. It helps us to improve on our results. Just to know, have a introduction to the lesson in front of the children. A rocket is supposed to get shot up like anything so that it leaves the Earth's gravity. What if the fuel burns too slowly? Don't you think that chemical kinetics is important at this point? If the fuel is going to burn too fast, it leads to an explosion. So reactions are important to us. Supposing you think of iron undergoing corrosion. Think of iron undergoing corrosion in matter of few seconds. How difficult it would be for us to manage the bridges. You are making use of the iron to make iron bridges, right? Which is an important part of our economy. What if the corrosion had been too fast? We would have never thought about putting iron into that kind of use. Similarly, supposing you are adding curd to milk and the reaction is too slow. It takes 3 to 4 days. Imagine, if I need the curd today, I would have to set up the curd 3 or 4 days back. So chemical kinetics helps us to understand the various factors governing the reactions and hence allows us to intervene the chemical reaction so that we can increase the yield and we can make it more economical. How else do you introduce chemical kinetics, teachers? In what other ways do you introduce chemical kinetics?
In physics, kinetics is very important. That means the velocity and speed, ma'am. Just like that, I start from the formula, speed is equal to distance by time. In that same way, the rate means the speed of the reaction is equal to amount of concentrations of reactants or products divided by time taken. In that way, I compare these two equations in physics and chemistry. Then
Yes.
only they can understand the basics, the definition or the importance of the kinetics, ma'am.
Kinetics. And how do you make them feel the importance of chemical kinetics? How do you make them feel the necessity of learning chemical kinetics?
You say more examples for slow and fast reactions, instantaneous reactions like that. When we cut apple, the color of the apple will be burnt. This is the
Yes.
oxidation reaction. But the corrosion is a very slow reaction. That way I explained the when we know the speed of the velocity, rate of the reaction only, we can prepare some industrial important compounds, ma'am.
Yes.
That is that's why we are studying kinetics, ma'am. Kinetics is where we can determine the amount of products by only by knowing kinetics, ma'am.
Yes, sir. Yes, sir. So what is the idea behind this discussion? Idea is like you're teaching some lessons in chemistry in class 11, class 12. Make them feel how they are related to them. Right? Make them feel why they are important to us. Make them close to the topic. Take them close to the topic. No, make them to physically realize why those topics are important to us. What is the use of it? Children after learning P block will tell us, ma'am, why are we learning so many reactions, ma'am? What is the use of it? If you can even pick out 1 or 2 reactions and make them realize that this is important for your daily life, this is important for the sustaining of the earth, then that makes them realize the importance of that particular topic, I feel. So make them close to the real life. Any topic for that matter. Like yesterday, ma'am was talking about biomolecules. Without biomolecules, I usually ponder over this thought. Before being dead, it is same biomolecules. After the death, it is the same biomolecules. So there is something in between. Respect the soul, which can feel. Okay, so take them closer to the topics. Make them feel the chemistry. So that is one way we can make them more interested in chemistry, first of all. Okay. So the goal of chemistry is to understand the macroscopic world by examining the molecular world. So it is this angle, right? We are trying to understand that the small changes that occur during the chemical reactions. So chemistry has developed so much so that we are able to intervene into the chemical reactions and sometimes we try to speed up the chemical reactions, sometimes we are able to slow down the chemical reactions. So we are entering the molecular world. So that is something which you can keep telling them and make them more interested in the topic. Okay, so as sir was saying, what is meant by rate of reaction? So normally they would understand the speed is equal to distance by time. Whenever they see a change around them, they say this change is fast, this change is slow. Take the chemistry close to that angle. So what you have to do is take the chemistry and say that the speed of chemical reaction in layman's term is nothing but speed. The rate of reaction is nothing but speed. And hence, how in physics you say distance by time is nothing but speed. Similarly, in chemistry also, you observe certain changes. So you are observing the changes in the concentration over time. Whenever you observe the changes in the concentration of the species involved, it may be the reactant or it may be the product over a certain time period, you are talking about the speed. So first define your speed is equal to distance by time. I feel that way they understand it better. For the first few classes, I don't use the term rate, I use the term speed. Speed is more relating to them than the term rate. Okay. So as we know that the rate of reaction is measured by change in concentration in a given time period. So relate to your terms used in physics. So that helps you to take them closer. So expressing the rate would be in terms of the product. Supposing the given reaction is A becoming the products, then in terms of products, the rate is del P by del T, and rate of reaction in terms of the reactant is minus del A by del T. So first role of us would be to say why this negative. Why this negative? And if this is put in minds of the children very clearly, they would never forget about why the need of putting that negative sign. We always know that, let us assume that if the starting material in the reaction is 10 moles, in the beginning it is 0. After a certain time, if this has gone down to, let us say 7, this would have increased to 3 if it is 1:1. Del P is always measured in terms of final minus initial. So it would be looking like 7 minus 10 over, let us say, a duration of 5 minutes. So it is going to give you a negative result. And at this point of time, please tell them that as in physics, the speed of a bus can never be minus 70 kilometers per hour. Am I right?
Yes.
Speed of the bus can be minimum 0, can be maximum of, let us say, 150, 200 if it is a super fast bus. But it can never become a negative value. So once you have told them the speed of a process can never be negative, they will also realize the need to put a negative sign. So instead of just telling them, whenever you are writing the reactants rate with respect to the reactants, put a negative sign, put a negative sign. Whenever you are writing the rate with respect to product, please write a positive sign. You have to keep telling them that this is 3 minus 0 by 5 minutes, which is automatically a positive value. Whereas here, give them certain values, let them substitute. After substituting, they would realize that the value is negative. And to nullify the effect of that, we introduce a negative sign. So make the speed of the reaction also appear positive. Yes, teachers, I hope all of us are doing this. So speed of reaction or rate of reaction, as I said, in the beginning of the classes, I use the term speed. Later on, once they have digested the fact that the speed of reaction is nothing but rate of reaction, I start using the term rate of reaction. So we can say that the rate of reaction is the rate of change of the products or rate of change of the reactants. Once you use the term rate, it is with respect to time. One mistake which children do often is that they would say that rate of reaction is the change in the concentration. That's it. They would forget about the time angle. If they forget about the time angle, then it is not rate. Do you agree, teachers? If they forget to mention about the time, it is no longer rate. Yes, the bus has traveled again 70 kilometers. It is different from 70 kilometers per hour. Make them to understand this fact. The bus has traveled 70 kilometers. The bus is traveling at 70 kilometers per hour. Make them understand the significance of time there. If the time factor is not brought in, it is just a distance. Once the time factor has been brought in, it becomes the rate. So when the children write the definition, we have seen during the correction that they would say the rate of reaction is change in the decrease in the concentration of the reactants, increase in the concentration of the products. And that does not give them any marks because they have forgotten about the time angle. Yes, teachers, this is one of the mistakes which we commonly see during the CBSE correction. So very important to say that it is rate of disappearance of the reactants or rate of appearance of the products, or you completely describe that it is change in the concentration of the reactants per unit time. Similarly, change in the concentration of the products per unit time. So these are some of the common mistakes that children do. Okay, so graphically, you have to make them understand that the del Y by del X, when you are substituting the concentration of the reactants versus time, what you are writing, what is the slope of this line happens to be the change in the del Y by del X, where the del Y represents the change in the concentration of either the reactants or the products. So let us put it as X by del T. If it is reactant, introduce a negative sign. If it is product, put a positive sign. Okay, so graphically make them understand. I feel there are 2-3 lessons wherein chemical kinetics is one lesson which deals with, since the topic is totally new to them, the first half of the lesson only describes, attempts to make the student understand about the topics more than teaching the concepts. So it deals with a lot of examples, graphical representations, calculations, and with the help of that, they try to understand that this slope is nothing but rate. So rate of the reaction is change in the concentration of the products or reactants with respect to certain time period, with a negative or positive duly attached to it. So make them understand the significance, because at some point of time, there may be a graphical question and they may be asked to answer certain questions, because one will agree that we are exhausting the questions. Over the years, the book has really got really old. From 2008, we are answering this book and the type of questions have got exhausted. So probably the setters also are looking for new questions. So make them give them complete understanding of the graphical representations. Okay, then how do you introduce, supposing the reaction is H2 plus I2 giving 2 HI, how do you introduce this fact that the rate is plus 1 by 2 change in the concentration of HI by del T? How do you introduce this fact, teachers? It's a very, what do you say, no, children do follow it in a, the way the instructions are given by us, they will definitely put it. That whenever you are writing the rate of reaction in terms of HI, take the coefficient, divide the change by 2, by that coefficient. But how do you make them understand? Teachers, I want your points, because everyone does by their own means. How do we make them understand? For example, if I take a reaction like A moles of A, B moles of B, C moles of C, D moles of D, then there is an important angle here. The rate is 1 by A times change in concentration of A with respect to time. 1 by B times the rate of change of B. 1 by C times rate of change of C. 1 by D times. How do you introduce this? Because it is something really tricky, I feel. How do you convince the children to put that coefficient here in the denominator? Teachers, please come out with your suggestions. How do you introduce? Because I do it in a way. Normally I do it in a way, but it will be so nice if I can get ideas from you. All of us will be benefited by this. How do you introduce the introduction of coefficient in the rate expression? Yes, teachers? How do you introduce? No, whenever there is a coefficient here, when you write the rate expression, we don't forget to put negative sign. Fine. Del A by del T. But why this A? Why not this A in the numerator? Why not this A in numerator? Or why not this A? Of course, there are reasons. Why not this A here? Because children have come out of chemical equilibrium. They might do all these. How do you convince the children that it should be in the denominator? How do you convince? So how I normally do is like how sir said, yes, that's one way. What I do is I normally take a small, I think I had made one slide for that. I'll see. I think it has gone somewhere. I think I've lost that slide. Yeah, see, what I normally do is I take a reaction. Say, for example, N2 plus 3H2 giving 2NH3. And I presume that I'm going to start with 6 moles of N2, 6 moles of H2. And at T is equal to 0, there is no amount of product. After some time duration, I assume that out of these 6 moles, 2 moles have reacted. The ratio here is 1:3. So if 2 moles of N2 have reacted, then it would have consumed 6 moles of H2. So 6 moles of H2 are gone. There is no amount of H2 left out. At the same time, I also see that 1 mole of N2 is going to form 2 moles of NH3. That means 2 moles of N2 which vanished from this should have produced 4 moles of NH3. Yes, teachers, up to this, any problem?
No, ma'am.
So what I tell them is that it looks for an observer, it looks like the decrease in the amount of N2 is less for an observer who is sitting outside. I'll put them as an observer and say that the decrease in the N2 seems to be less, whereas the decrease in the H2 seems to be enormous because the H2 is completely gone. It's vanished. But the reaction is going to travel at the same speed. It's something like I'm sitting in a bus, my bag is there in the bus, my kid is there in the bus, and somebody else has got 2 bags and 3 kids probably. And if the bus is traveling at the speed of 70 kilometers per hour, everybody is going to travel at the same speed. So it doesn't matter whether the substance vanishing are less or more. Apparently they are different. So how do you convince? Supposing I take the same data and plot it on the rate expression. Then it is final 4 minus initial 6 in 1 minute, which is 2. So rate of change with respect to N2 is 2. And if I ignore the coefficient, it is final 0, initial 6, 0 minus 6 with a negative sign is 6. So rate looks to be 3 times that of rate of change of N2. The rate of change of H2 seems to be 3 times that of rate of change of N2. And the rate of appearance of N2, NH3 seems to be 2 times the rate of disappearance of N2. Now, as I told, all of us are traveling in the same bus. This is one reaction and all these are the reactants and products involved in the same reaction. So how can the rate be different for N2, H2 and NH3? So what should be done? Divide this by 3, divide this by 2 and introduce the fact that this 3 is nothing but the coefficient 3 here. And this 2 is nothing but the coefficient 2 here. Yes, teachers, is it right, teachers?
Yes,
A
ma'am.
little more mathematical, but I think at the end of the day, they will realize that the coefficients must divide the entire change in the concentration. So again, I'm telling you, it is Like, no, how I feel, how you make the children feel. The chemistry should not look like chemistry. They should feel more of, no, the physical connect. So take these kind of small examples. It can be very simple example, right? Very simple examples. It's like, no, I used to tell them that if there is a catalyst which is heterogeneous catalysis process is going on. So I just give them examples. How does this, we all tell that catalyst is going to lower the activation energy. Catalyst offers surface for the reaction to happen. Catalyst makes intermediates, and thus unstable bonds are there. All that is chemistry, yes. But what I tell them is, like, I have got certain balloons. What is the probability that this balloon will hit this balloon? And only if there are collisions, the reaction would happen. So what is the probability that this balloon would hit this balloon? The balloons are not tied to anything, and hence they are free to move in different directions. What if these balloons are tied on this catalytic surface? Do they have more probability of having the interaction?
No.
Before and after being tied to the surface? In which scenario? In scenario A, where they are loose, not bound to anybody, or in B, where the balloons are attached to these metal surfaces. Where is the chance of greater collision between the balloons? In scenario A or scenario B?
Scenario B.
B. And thus you are increasing the concentration. You are allowing them to interact. You are providing a surface for them to collide, break some older bonds and create newer bonds. Am I right, teachers? What did we do? We converted chemistry into something which we normally see around us. Yes, teachers? So what is this surface? This is a catalyst. This is the heterogeneous catalyst. What does it do? It binds all the reactants, allows them greater proximity and hence reaction. So every time you do, no, you connect the chemistry with something which is close to their life, something which they can realize. Because as Radha ma'am was saying, some children will finally come and tell that, ma'am, had you shown us the book, we would have not taken chemistry or science group at all. How do we make them comfortable? Is by making them close to the chemistry through these small things. These are not, every time the example will change, I feel. Next time when we go to the class, some other example will come to our minds. And we try to make the things easier. Yes, teachers? So the importance of this coefficient here in the denominator is emphasized thus. Okay. So how do we talk about instantaneous rate and average rate? Take a graph, talk about a small time period, observe the del y by del x and call it out as instantaneous rate. And if the time period is large, you say that. So you also use a small d of the reactant by dt, right, to indicate instantaneous rate, and del to indicate the average rate. So this itself tells them that the change what we are observing is over a very small time period, and here it is for a larger time period. So instantaneous rate and average rate. I think they don't have any difficulty in understanding this. So I had given some questions here where the importance of introducing negative sign and all that. I think I will not spend much time on this. I thought we will do some questions. But if you can read the questions and tell me if there is any problem, then we will try to do. Otherwise, I think we will just move. Express the rate in terms of change in concentration of reactants and products. In the first 15 seconds, 0.015 moles of O2 is produced in 0.500 liters reaction vessel. Remember, it's the quantity and the volume. It's not the concentration. So we will have to first find the concentration divided by the time period to determine the rate. And since it's O2, children will automatically go and check what is the coefficient, and hence will not miss out if there were any coefficient, they would definitely introduce. Okay, what is the change in concentration of N2O over the del T during the same time interval? So this need not have been given because it says during the same time interval. Either you talk about the products and time, or you talk about the rate. In any way, you have to introduce. So best is to, I think these are not a problem because the amount divided by the volume will tell me about the concentration. Concentration divided by the time period. Since O2 is the product there, a positive sign will tell me the rate of reaction. So it's a straightforward question. Probably children will misrepresent these terms. I normally tell them that supposing the reaction is this, including 2, it is rate of reaction. Excluding 2, it is just simply the rate of disappearance. So you have to put this idea behind it. So do a number of exercises, right? When you minus del of N2O by del T, it is just rate of disappearance of N2O. The moment you introduce 2, the coefficient there, it becomes the rate value. So give them that clarity because child will know to calculate, but the child will get confused as to what he is supposed to calculate. So in such questions, go back to the question, read it out. What is del N2O by del T during the same time interval? So let them read. This is norm. This is given in expression form, but in one of your NCERT text questions, it says, what is the rate of disappearance of? And children are ready to do the calculation because they've understood, but they would not know what are they finding out. So write the expressions multiple times in the class. Say that this is the rate of appearance of O2 as well as the rate of reaction, whereas minus and this much is the rate of disappearance of N2O. And if you include 2, it becomes the rate of reaction. So give them that clarity a number of times. Take a number of examples and provide them that expression because this is one of the frequently asked questions. Rate of production of N2. Rate of production of N2 will become plus 1 by 2 times del N2 concentration by del T. Whereas rate of reaction, this is rate of reaction, whereas only the rate of production of N2 would become the change in the composition of N2 in the given time period. So give them that clarity as to what it means to introduce the coefficient. The moment you introduce the coefficient, it becomes the rate term. Excluding the coefficient, it is just the rate of appearance or rate of disappearance. So take number of examples and do this. So I've taken some more examples, but I think we will run out of time if we do all these. Factors that affect the rate of chemical reaction. I feel all of us, this is one of the very famous questions. Earlier, we used to have that a large log of wood wouldn't burn so easily as a matchstick, even though both have same matter to burn. So we would bring in the concept of surface area or state of subdivision. Larger the surface area, greater the reaction. So again, you can know, take some day-to-day life experiences and talk about how surface area makes a lot of difference in reactions. Okay, I think again the same. So let us actually the other area which is sometimes no children feel it difficult would be the graphical representation. So we'll just quickly go to the rate law. Okay, this is another expression. Yeah. What is rate? What is rate expression? What is rate law? Right? More or less for a child who is beginning with the chemical kinetics, things almost seem similar. So we need to make a clear difference as to what is rate. Rate is the production of the products or loss of reactants over time. So this part, please try to emphasize or introduce the term rate of production of the products or rate of loss of the reactants, disappearance. So either you use the term rate or you put it in terms of time. So either way, it should emphasize upon the time taken for the process to happen. What is rate reaction? Rate expression would be how to write how to write this. In fact, when we go into the CBSE cases, even the differential form of rate equation is also very, very important. Differential form sometimes they ask. Rate law. Rate law is the clear definition of rate law, because what is rate law? What is rate constant? These are some of the frequently asked questions, and the clarity is required. Whenever we correct the papers, we see if one or two parts of the definition is missing out, the child loses all the marks. So when you are trying to define the rate, let them pick the rate expression of an imaginary reaction and try to speak it out. That rate of reaction is directly proportional to the concentration of the reacting species raised to some power which may be or may not be equal to the stoichiometric coefficients. So let them take out the expression instead of memorizing. When they memorize, the child with a greater stamina will memorize till the end. A child who is not, is impatient and is not very much good at memorization will forget half of the statement. So instead, let them pick out the rate expression, rate law expression, and try to define the expression in his own words. That will complete it. Okay, another way of looking at it is actually when we spoke about the factors affecting the rate, we normally take in the effect of concentration first. Then we take up the effect of temperature. We also talk about effect of catalyst, right? Also in terms of collision theory, we talk about how temperature plays role and all that. Now, when you are trying to talk about this rate law, I normally try to tell them that the concentration part, supposing I take this expression, the concentration part is this half. This is the concentration part affecting the rate of reaction. And the K here, who is sitting silently, deals with the effect of temperature on the rate. Later on, when we introduce the Arrhenius equation, we say that K is equal to A e to the power minus EA by RT. So we know that K is proportional to e to the power minus EA by RT. So we know that the T defines the K. T determines the K. So when you are introducing the factors, you tell them that though the rate law has a constant K and a concentration term, you tell them that wait for the future classes, this K is going to bear the effect of temperature on the rate. So this actually prepares them for the second half of the lesson. The first part of the lesson is basically the effect of concentration. So here itself, you give them a prelude that the K is going to tell you. And at this point of time, you keep telling that the K depends only on temperature and it does not depend on concentration or pressure or any other factor, like equilibrium constant. So it is a recollection of equilibrium concept also, that the K value, equilibrium constant or the rate constant here, will depend only on temperature, will change with change in temperature and with nothing else. So keep telling this idea so that it gets reinforced in their brains. The moment you say K changes only with, they should be able to tell that temperature. They should be able to fill in the blank that it is going to change with temperature. So that way, the emphasis on K factor. Another common question, very common question and very commonly made mistake. I won't call it made mistake because the book does not specify the definition of K, but the CBSE definitely asks the definition of K again and again. How do you define K, teachers? How do you define the rate constant? Do we say that it is the proportionality constant? Is it right to say that it is the proportionality constant? Because according to the law of mass action, we say rate is proportional to the concentration of reacting species to some power which may not be equal to the stoichiometric coefficient. So do we say that it is the proportionality constant? Is it right? Or is there any other way? I'm sure those who are going for the CBSE evaluation will definitely know. Those who have not gone for the CBSE evaluation, those who have not faced, maybe the question is only for them. How do you define K, teachers?
Concentration of the reactants if you take 1 molar, ma'am.
Very correct, sir. Very correct. It is the rate of reaction when the concentration of the reactants is taken as 1 unit or 1 mole per liter or unity. or for 1 molar solution, 1 molar solution. So the definition of K, children often tend to write, because the way book describes, it says law of mass action says rate is proportional to a to the power, and then it says that K is introduced, it's the proportionality constant. So children end up saying that the K is proportionality constant. It is the ratio of rate to the concentration. I would agree. It is the rate, right? If you are going to take off this term here and you put it in the denominator side, then it is ratio of rate to concentration of the reactant to the power n. So it is correct, but I doubt whether the CBSE agrees with this. Am I right? Am I right, Sindhu ma'am? Radha ma'am, am I right?
Yes, ma'am. Yes, they don't go in for this. We have to write as told earlier.
Yes.
But actually it makes sense, no?
Yes.
K is the ratio of, but there are definitely some problems with the CBSE way of setting the scoring key also, and teachers are made to think on the lines of the scoring key always. But still, technically, if the child is preparing for an entrance examination, tell them it is no different from the rate constant.
Usually have this discussion during the corrections now always.
Yes, yes. So we feel that the child has written correctly, but we are unable to give marks just because the scoring key is telling that way. So these are some of the points where the children can go wrong. Okay. How do you introduce this? Okay. There is another very crucial thing that we have only the 0 and the first order reactions. We don't have second order reactions. Okay. But yet we need to understand that rate is proportional to a to the power 2. That is A representing the reactant, A, let us say, becoming product. So where is this going to be relevant? Whenever we try to plot a graph, right? Let us put it as rate versus concentration. Okay. Okay. Rate versus concentration. Supposing with a change in concentration, the rate value remains the same. Then what is the order of this reaction, teachers?
0.
0 order reaction. Okay. How will the expression look like if I put A to the power 1? What will it look like? Supposing the reaction is a first order reaction and I plot rate versus A to the power 1. Reaction is a second order reaction. I plot rate versus A to the power 2. What do they look like? Let us go to the rate law itself. Can we put it as y is equal to m into x plus c? Whenever there is a graphical question, please try to do this. Try to put the reaction into y is because we are expecting straight lines. Y is equal to m and y is equal to mx plus c. So what we have done is on the y-axis, we have plotted the rate. On the x-axis, a square, provided it is a second order reaction. So what is the value of the intercept? It is 0. So it should start from here, from the origin. And it's a constant k. So it's going to look like this. Yes, teachers? Similarly, if it is a first order reaction, it's going to look like this. And in a way, this becomes a check. Supposing the reaction is a second order reaction. Supposing the reaction is a second order reaction and you are trying to plot rate versus A to the power 1. Right? What you would not get is a, can you complete? Supposing the reaction is a second order reaction, but you are trying to plot rate versus A to the power 1. What will you not get? You wouldn't get a straight line only if rate versus A to the power 1 is plotted for a first order reaction. The reaction I told you is a second order reaction, but you are trying to force it on a rate versus A to the power 1. Will you get a straight line, teachers? Will you get a straight line? Yes, teachers. Would you get a straight line? What am I trying to lead you into? I'm trying to tell you that this becomes a check. If the reaction is a first order reaction, rate versus a to the power 1 must be a straight line. If it is a second order reaction, rate versus a to the power 2 should be a straight line. Now you try to mismatch. The reaction is a second order reaction, but you are trying to plot it on R versus a to the power 1. You wouldn't get a straight line. What does it tell you? It tells you that it is not a
First order reaction.
that's all. This gives you a check. This gives you a check. Supposing the reaction is a first order reaction and you're trying to plot rate versus a to the power 2, you wouldn't get a straight line. So this is you slowly make them move into the chemistry and slowly, make them think critically. That critical thinking is very, very important, though it is not going to be asked in the examination, but definitely their aptitude develops. Some of the brighter ones in the class definitely would take a lot of interest in chemistry. Instead of thinking chemistry as a dry subject, they would definitely take more interest. If one or two is able to answer this question, others will be interested in it. That okay, this fellow is able to answer. Why am I not able to answer? So try to collect some questions of this sort. Okay. How do you teach them rate determining step? It is, the definition says it is the slowest step. It's very easy to make them realize. What examples do you take, teachers, to make them realize that it is the slowest step, which is rate determining step? How do you introduce? Because we have, as Radha ma'am was saying, there are very few occasions to make our classes little lighter. So can we take this as an example?
Yes, ma'am. Can I try, ma'am?
Yes, sir. Yes, sir.
When two horses attached in a vandi, just like
Yes,
a
sir.
cart.
Yes.
When one horse leg is affected by some problem or some pain, the rate of the cart is determined by the cart which is moving or walking slow, running slow, ma'am.
Very nice.
That is an example I'm already giving
Excellent, sir.
in my
Excellent.
class, ma'am.
Excellent, sir. I think I will
Thank you,
also
ma'am.
start using this example.
Thank you, ma'am.
Excellent, sir. Any other examples that we use to make the children realize that the slowest step becomes the rate determining step?
Ma'am, if I may.
Yes, sir. Yes, ma'am.
Ma'am, the classical textbook example is one that I think they relate to easiest. The slowest runner of the four
relay race
teams in a relay determines the fate of the race.
Yes.
Because most of them watch relay or they run a part of the relay team.
Yes.
So when you say that, you shouldn't compare the members of the same team. You have to compare the slowest member of each team.
Yes.
The slowest runner, and strategically ask them if they could place, ma'am, even an activity dividing them into groups and choose the slowest runner to decide the rate. That way also we can do a drill project, ma'am, for this.
Yes. Excellent, ma'am. Yeah, these are really good examples. No, these are the areas where we can bring them close to chemistry. What I'm trying to tell you is make them feel that they are not doing something very, very difficult. They are doing something which is quite manageable. So that confidence, if you give, children will automatically start and try to work on that. So what I normally tell them is like, say you are coming to school and you are going to stop at a number of signals. One signal is released at, let us say, 10 seconds. Other signal is released at, let us say, 2 minutes. Another signal is going to hold you back for another 5 seconds. So which signal delayed you? Right? You are coming to school is decided by which of the critical signals. And towards which signal do you keep praying that, oh God, let the signal quickly open up? They would automatically point out that signal which held you back for a longest time. But I feel that both the examples which teachers give, very nice examples. So they are going to take that subject very lightly in that case, in such physical example cases. Okay, rate, I feel these also we can just quickly do, but some of the questions, yeah, this is one of the question. I just collected it with the year and all. The C represents the compartment. Sometimes there are questions where the rate constant is mentioned and they are asked to identify. Sometimes there are questions. So in such cases, we look at the unit. We look at the unit and decide upon the overall order of the reaction. So I think we can move. Yeah. Yeah. Reactions, when we talk about the mechanisms, we need to talk about the reactions which are elementary and which are complex. So again, the idea behind elementary and the complex reactions must be introduced in a proper way so that they understand. This was just a representation of the signals. I just got a picture of that and I thought I'll put it here. So this is just an application of that, teachers. As I said in the beginning, I tried to collect questions as we discuss the concepts. I wanted to put them here. So it is about that the slowest step is going to be the rate determining step. And the rate law, this is a nice, maybe you can have n number of examples. If you are looking into the internet, you get a lot of examples. This is, I think, from the exemplar. When you try to write the rate law, you would write the reaction looks like H2O2 is producing 2 H2O and O2, and it has got nothing to do with I minus. It looks like that. But we have all seen that volcano activity, which normally any science activity person will be doing. He would take hydrogen peroxide, put a little amount of potassium iodide and throw off the foam, because oxygen gas is given out. So it looks like a bursting, erupting volcano. So you can take that example and tell them that they need not know these steps, but at least give them these steps and tell them that this is how the reaction goes. Pick the slowest step and try to write the slowest step. So when you're writing the slowest step, you would say that rate is equal to K into the concentrations of the species involved in the slow step to the power, which is same as these coefficients. Now we can claim that the coefficients are same as these because it is the slowest step. So for I normally tell them that 99, the further discussion is about the molecularity. I tell them normally that the molecularity and the order of reaction is same in the reactions which are marked as the rate determining step. The molecularity and the order of reaction value would be same for the rate determining step in 99.9% cases. I would always put that 99.9% cases because they need to understand that for a zero order reaction also, there would be a slow step. And we all know that molecularity of any reaction cannot be zero. So for a zero order reaction, the rate determining step will have a certain reactant, will have certain coefficient, but that coefficient is not equal to the order because order is already told that it is a zero order reaction. So when you are talking about a zero order reaction, first let us at least talk this in very clear terms. If it is a complex reaction, the slowest step becomes the rate determining step. And for the rate, with the rate determining step, we write the rate law. So what we do is we pick the reacting terms and pick the coefficients, and without hesitation, we put it here. It is unlike the rate definition that we were giving so long. We were saying that it is the rate is proportional to the concentration of reactant raised to some power, which may or may not be equal to. So here we are not saying may not be, we are saying it is 1. Why? Because we have already identified the rate law. We have already identified the slowest step. Then we come to the point that the molecularity is not same as the order in 99% cases. The exception is immediate exception. You can talk in terms of zero order reaction where the order is 0, but the molecularity Can it be equal to 0, teachers? Can it be equal to 0? No way. So molecularity cannot be equal to 0, but the order is 0. So for a 0 order reaction, the rate determining step, right, will have certain molecularity, but order of reaction is 0. So in 0 order reaction, the order and the molecularity value will definitely change. So you can always say that in the complex reactions, right, whenever a reaction is happening in a complex way, complex is, that is a reaction happening in a number of steps, the sum of the coefficients of the reactants is equal to the order, and the order itself is the molecularity. So that clarity you have to give them, that molecularity is same as the order for rate determining step, excepting for the 0 order reactions. So in fact, there were questions sometimes. I think I had collected one of the question. Yeah, here. For which type of reactions order and molecularity have the same value? What can be the answer, teachers, here? For which type of reactions order and molecularity have the same value?
Elementary reactions.
Elementary reactions, which happen in one step. The values are same. Okay. Give an example of a reaction in which order and molecularity are different. Can we give any catalytic reaction where the order is 0, but molecularity is not 0? Yes, teachers?
Pseudo order reaction.
Yes, yes. Yes, pseudo first
Pseudo first
order
order
reactions. Yes, very nice, sir. Good. Okay, what about this question, teachers? Am I able to show you fully?
With respect to A first order, madam. With respect to B 3/2 order, madam.
3/2. Can this reaction be an elementary reaction, teachers?
No, madam.
No. Why so, sir?
Why? Because if you have taken acetaldehyde
Hmm.
in single step, this kind of fractional order will not come. Single step.
Okay, but what if it is a board question, sir? How do you answer this question? You can't take an example and say, right, sir? Like acetaldehyde, sometimes even the examiners wouldn't know what is happening with acetaldehyde.
Yes, sir.
So what will be the convincing way to answer this question, sir? Can this reaction be an elementary reaction? The rate law being given.
Okay, you only explain.
Yes, anybody else, teachers? How would you justify the answer of this question? What would be, what did I just now say? That the, we were here, we were saying that the value of the sum of the coefficients of the rate determining step will be equal to the order and the molecularity in 99.9% cases. The sum of the coefficients is equal to the order and the molecularity. So what is the coefficient here? The coefficient should have been 1, coefficient should have been 3/2. So it is 1 plus 3/2, which makes it 5/2. Can the molecularity have a value of 5/2, sir? Can the molecularity have a value of 5/2?
No, ma'am.
No way. What are the possible values of molecularity? 1,
2, 3.
2, or maximum of 3. So the statement goes wrong. What is the statement? We said that the sum of the exponents in the rate law would be same as the sum of the coefficients in the rate determining step. So since the sum of the coefficients comes out to be a fractional value, molecularity cannot be a fractional value. It has to be a whole number. Obviously, this is not an elementary reaction. These type of questions, no, there is a discussion about a reaction happening in the gaseous phase, and children often find it difficult. Even when we give this question in our internal papers, children do lose marks. So I think we have to communicate this clearly as to why this is happening, why the first doubt in the minds of children will be that if the reaction is taking place, how come the pressure is increasing? We have always seen that the reactants becoming products, towards the progress of the reaction, the concentration of the reactants would always decrease. So children are fixed with that idea, but here they are confused with why the 35 mm of Hg is increasing to 54 and then going to 63. So they would be definitely getting, at least this is one area which I find difficult to convince them. Then when we say that this is gaseous, any decrease here is also an increase. So the P total is because of the left out amount of reactant plus newly added product. Then they agree, yes, ma'am, it may be because of some more products that are formed. So they get convinced that there is a more pressure progressively with the increase in time. I thought we will do these two, but again, no, I think there is no time for that. Okay, calculate the rate of reaction. I feel here also when we talk about this, we say that it is K into the concentration of SO2 Cl2. The K value would be found out like how we did in this case. But how to convince them this is nothing but Pi minus 2 Pi minus P total. I feel when we do these things, I think I'll have to go to the same topic again. Yeah, when we write the expression here, when we say that T is equal to 2.303 by K log of A naught by AT, I feel one of the very, very important duty is to keep defining what is this AT. What is this AT? Very, very important that we keep defining number of times. Often children get confused whether it is the amount left out or amount reduced. Amount left out, amount reduced. Keep telling them that this is the amount left out. So when you are doing this type of a problem, we normally use the term, the pressure. In the pressure cases, we say that it is Pi by 2 Pi minus P total. So here itself, try to tell them that this 2 Pi minus P total is nothing but 80, which is the amount left out. Amount left out, amount left out. And if you keep telling them this, finally, when you do it here, we also should convince the children that as we continue with the reaction, the rate of reaction is definitely going to dip down. Why do you think that the rate of reaction will go down, teachers, with the time? And that's how the initial concentration cannot go into this value. It has to be something else. It has to be concentration at a certain time t, 2 Pi minus P total. So why do you think that the rate of reaction will fall down with the time? Why do you think rate of reaction will come down with the time?
Maybe
Is it-
the collisions are lesser.
Yes, sir.
Ma'am.
Yes.
By collision theory, that's why the rate may be decreased, ma'am.
Very true, sir. With the time, the reactants are converted to products. So the amount of reactants in the beginning is definitely going to decrease as the reaction progresses. So after a certain period of time, there are probably very few reactants left out to collide. And hence the rate of reaction is bound to dip. It has to dip. It has to come down. So you tell them that this term cannot be 0.5. Why? Because 0.5 was the concentration of the reactant in the initial time. And after passage of time, right, this term has to decrease. The rate is no longer dependent only on the initial concentration of the reactant. It is dependent on the left out amount. So again, the concept of left out amount of reactant has to be brought in. So recollect, what expression did you use for left out amount? 80. If the reaction is gaseous, what did you substitute in the place of 80? 2 Pi minus P total. So for this reaction, once you have found out the K, 2 Pi minus P total into the K will tell me the rate. So this is one question I feel all the children, irrespective of batches, I have seen this question, they find it little difficult. So it is how we, instead of just writing the steps, convince them. What was 80? What is AT? The amount of reactant left out. What was the expression you substituted for AT for gaseous reaction? 2pi minus P total. And then convince them that this is how the question goes. Also put in a word that the 2pi minus P total is also variable. If the number of products are different, this expression will also change. So take 1 or 2 examples where A is breaking down into B plus C. This is given in the text. Take one more term in the product side. Work it out as to how this expression will change, so that they know, they realize the concepts. Instead of just memorizing the concepts and just memorizing the way to do the sums, they get a conceptual clarity. Once they are conceptually clear, the sums will not go wrong. Here and there, they may do silly mistakes, right? Okay. I think I have got a lot, but this was one of the discussion which I had kept. Okay, this can be left out. The concept of T half. We know that T half is independent of concentration of reactant in the case of first order, whereas T half is directly proportional to the concentration of reactant to the power 1 in the case of zero order. So this term, there are many questions possible where somebody says that the amount of reactant gets reduced to half in 5 minutes, then get reduced to 1/4 in another 5 minutes. So 5, when they say 5 minutes and 5 minutes, the T half is constant. If T half is constant, the reaction must be first order reaction. So that kind of understanding has to be provided, right? Don't just say that it is independent of A, not directly proportional to A, but instead give them some examples. Supposing you take 10 grams to reduce into 5 grams, it is taking 2 minutes. Supposing 5 grams to reduce to 2.5 grams is taking 1 minute. Then we know that initially it took 2 minutes, now it is taking 1 minute. That means the T half time is reducing. And if T half is reducing, it's no longer constant. It's proportional to A naught, more the A naught, more the T half, less the A, less the T half. Tell them that it is a zero order reaction. So these kind of interpretations you have to make so that they understand the concepts very clearly. Another thing which we often, the children go wrong is, sometimes we also miss these terms and we also go wrong, that concentration of A falls to, reduces by. These terms have to be very, very carefully handled. As I said, it is log of A naught by AT. Keep defining what is this AT. Keep saying that it is amount left out. So when they say A falls from this to this, the reactant is falling from 0.1 to 0.075. Then let them know, just it's English, that this is the amount left out. This is the initial. From this to this, it is falling. So this is left out. So amount of reactant left out. Just put in this idea of what is AT again and again, I feel. Okay, pseudo first order reaction or pseudo order, because the topic says pseudo order. Also make them understand that it is not just a bimolecular reaction becoming a more order 1 reaction. It can also be third trimolecular reaction behaving as a second order reaction. So extrapolate the idea. Just don't restrict them to pseudo first order. Take them to pseudo second order, third order, and give them examples. Give them a lot of examples here also. I normally give examples to just to make them realize that the amount of water is so large that change in its concentration will not affect the rate. So keep telling them, and this can be done with a number of examples in our daily life. Okay. Okay. How do you explain this graph, teachers? How do you explain this graph? What examples do you take to explain this graph? The dependence of reaction on the temperature, the Maxwell-Boltzmann distribution. Of course, this term is not there, but anyway, it is that. So how do you explain this, teachers? How do you explain this?
Based on the classroom connection, ma'am.
Yes.
Madam, fraction of molecules.
Yes.
Molecules are, if it is higher, the temperature will be very low and kinetic energy also will be lower.
Okay.
And that red line, that red graph, that red curve indicates that fraction of molecules when compared to lower temperature will be higher. At higher temperature, even kinetic energy also will be little higher. Why? Because the collision between the molecules and walls of the container will be rises.
Yes.
Okay, ma'am.
Yes.
That is we can say from the graph, madam.
Yes, so that's concept. And how do we tell the children? How do
Ma'am, in
Yeah,
one
yes.
classroom, ma'am,
Yes, sir.
many students are there. Some students are toppers, some students are
Very
slow
good, sir.
learners,
Yes, sir.
some students are average is there, no, ma'am. Like that, we can explain. Ma'am.
Yes, sir.
Toppers are very rare only, ma'am. Very less members only.
Yes. Yes.
Slow learners also very less, but moderate members are more, ma'am.
Yes, sir. Yes, sir. And what
we
I
are-
normally do is, yes, same example I take. I will tell them that this is the distribution of marks in the beginning of the revision exams. In the beginning of the revision exams. And with lot of revisions going in, lot of hard work which you put in. Okay, that way I can put in the value point also. That you cooperate with teachers. The teachers will do good to you. The teachers will make sure that you learn more. You cooperate, and when you cooperate, the distribution of the marks will move to the right. So if
Yes.
this is, let us say, the passing marks, of course, passing marks, maybe for some children it is difficult. So maybe to boost up their morale, I would say this is 70 on 70, or let us put it as 60 on 70. So there were very few who are scoring 60 on 70. With more and more revision, with more and more cooperation you render to the teacher, with more and more hard work. So the temperature, lower temperature to higher temperature, I would put it in the form of more greater sincerity that you offer towards the subject and towards the preparation. Obviously, everyone's marks is going to shift on the right. So the children who score 30 would score 40, 40 would score 50. Those who are scoring 55 would score 70. So greater number of children come into the region, come into the tree of getting more and more marks, instead of a very few who were doing it initially. So the classroom behavior, no, there you can really modify. You can you can give it nicely, and children do cooperate, sir. So these are some of the areas I feel I'm extending some of the questions. I felt one of the, how do you feel this question, teachers? You are able to make the children feel comfortable with these questions? Yes.
Yes, ma'am.
Does this K trouble you ever? This K here? Why this K here? When I started teaching, I used to wonder what is this K doing here? But later on, we realized it is the Kelvin, and it will eventually get cancelled. So I feel every teacher would face these kind of troubles. So what is the precaution? This children often, this is very, I would say, very least probable question in the board examination, because it involves a number of steps, and the level of understanding required to do this question is also very high. But what I want to emphasize here is that the question is asking you to calculate EA, and at what temperature will its half-life period be 256 minutes. And you are going to make use of Arrhenius equation. And in Arrhenius equation, the moment you use the term EA, EA is represented in joules per mole, which is SI units. So when you are going to use the data for this time period, it is mandatory that you convert this also to seconds. So that is one area which goes wrong. Yes, teachers? So at this point, conversion of that time into seconds is very, very important. Though this question luckily has not been asked in the board examination, this is a textual question, but I feel this is where children would go wrong. Okay, this is another tricky. I think one question I had, yeah. This is one of the questions. Which of the following statement is not correct for a catalyst? I feel I should expand it out for you people to read. Yeah, it catalyzes the forward and the backward reaction to the same extent. Yeah, the question is which is not correct. So it does, right? It alters the del G. This is del G. Does it alter the del G of the reaction, teachers? This was once upon a time one board question. What is the influence of introducing a catalyst on the del G of the reaction? And why del G, even del H? Even del H. So what is the effect of introducing a catalyst on the del G of the reaction or del H of the reaction? Do you think that it is going to change, teachers, the del G of the reaction? Does it
No.
change that? No. So answer is a clear cut no. It does not change, because when we plot the graph of the energy versus the state of the reactants or products, let us say it is an exothermic reaction, the del G is after all this difference. So whether the peak is this high or even higher, whatever it is, the total del G is a state function. The del G changes a state function. It depends upon the initial and the final state. And hence, it will not be affected by the catalyst. What does the catalyst do? The catalyst is going to provide a number of theories are there. You can just correlate all those theories by this chemical kinetics. Of course, we do it in the beginning of the 12th standard, but you can just put in the seed of lowering the activation energy, providing an alternate path with the lower activation energy, providing surface for the reaction to happen, intermediate formation. At this point, you can put in all the catalysts, right? Everything here, right? Make them comfortable so that they are prepared for the others. Okay, graphical parts. As I told you, whenever there is a graphical question, it is best to convert it into the y is equal to mx plus c format. That's how it is to be done. No other great thing in that. So for example, if this is your y and you are plotting, that is ln A or ln R versus t, then this is your x, this is your slope minus k, and this must be your constant, that is intercept on the y-axis. So make this, try to give them with the ln, with the log and ln, they make mistakes a lot of, when you are using the term ln, you are not incorporating the 2.303 factor. When you convert it into log to the base 10, from log to the base e, the conversion factor comes into play. So the same term, supposing this had been log, this would have been k by 2.303. Minus k by 2.303. So make them do, you have to give them the equation. Do not teach the graph just by showing the graph. It is a bad idea. You give them the equation, try to give your y-axis, m-axis, make them plot. If there is no intercept, let them start it from the origin. So this is, they all know from maths. It's not that we are going to teach mathematics, but we are going to connect the mathematics with the chemistry. So children who are interested in maths will definitely find the connect. Children who are not even connected with maths will find this more easier than maths. So these kind of things make the, I feel will make the study more comfortable to them. I think I had a lot more, but any other point that we are missing, teachers? Any other point that we are missing? Activated complex. Yeah, the same thing here. If you are plotting the graph for ln k versus 1 by t, the ln term, then it is minus EA by R would be your slope. Supposing it is log, then it's going to be 1 additional 2.303. So instead of teaching them this is y-axis, memorize this as 1 by t, this is to start from here, end here, nothing like that. Give them the equation, make them to plot the graph theoretically. Make them to understand. So that only will make the lesson more clearer. So what were the objectives that we were targeting? That the child will be able to define average and instantaneous rate, express the rate of reaction in terms of change in concentration of either the reactants or the products with the time, distinguish between elementary and complex reaction, molecularity and order of the reaction, define rate constant, dependence of rate of reaction on concentration, temperature, and catalyst.
Madam?
Derive. Yes, sir. Yes, sir.
Madam, I have one small doubt, madam.
Yes, sir.
In when you are defining a rate, in formation of ammonia, N2 plus 3H2 gives rise to 2NH3.
Yes, sir.
In that, when you are writing rate, why we are writing 3 moles of hydrogen will be written as -1/3, madam?
Just I told you here, sir. I was using a balloon-like picture there to represent it, sir. You remember, sir? We have to tell them that, yeah. I was telling them, can the bus travel with a speed of -70 kilometers per hour, sir?
Okay, madam.
Can the speed of the reaction be negative? Can the speed of any
No, no,
process
no.
be negative? Can the bus travel at a speed of -70? Not possible.
Not
So I
possible.
took this example where I said that when you are calculating the same, the one which you are asking, right? If it is
Yes.
3 moles of H2, I took a hypothetical scenario where initially it is 6 moles of H2 becoming 0. So when you calculate the del of the reactant by del T, we say that final amount minus initial. So final amount is 0, initial amount is 6. By time taken, I took the time duration for this change to be 1. What do I get here? -6. This happens to be the speed. As I told you in the beginning, we say speed is rate. So can the speed be negative? Can the speed of any process be negative?
Speed, no, ma'am.
No. So what do we do to nullify this negative, sir? I can't have the speed with a negative sign, no, sir.
Okay.
So what do? We introduce a negative here to nullify that effect. So we'll say it is +6.
Okay.
So why do we introduce a negative sign when we are writing nitrogen, hydrogen terms related to rate? Is because we know that the final amount of reactant is less than the initial amount. So if I had not introduced, it would have looked like 4 minus 6. 4 in the final, 6 in the initial. So 4 minus 6, which is -2. I know that speed cannot be negative. So what should I do to nullify that effect? I would introduce a negative sign. So minus into minus is plus. So it is +2 moles per liter per second.
Okay. Thank you,
And
madam.
why 3 we already told. So that the rate of disappearance of the product or the reactant is not wrongly read. All the things are happening at the same speed, and hence the coefficient there. Yes. I hope I have clarified that, sir.
Yes, madam. Got it.
Yeah. Then what were the other things? Yeah, rate constants for the 0th and the first. I think we didn't do elaborately these collision theories and the importance of chemical kinetics on our daily life, and appreciate the kinetic angle of the reaction. The idea behind teaching why chemical kinetics should be taught is for every reaction there are two sides, the thermodynamic side and the chemical reactions, the chemical quickness. Like we know, ammonia production is fast. Theoretically, if the temperature is high, the reaction should slow down. Le-Chatelier principle says that introduction of heat will slow down the product formation, but we want the products faster, and hence we intervene into the reaction and we try to modify the reactions. So idea behind chemical kinetics will be that in future children can take up chemistry as their future course of study, and these are small introduction to various aspects of chemistry.